Welcome back to Science Modernizers. Welcome back to this video. In today's video, we are going to see a new lesson which entails both mathematics and further mathematics. So it is known as curve sketching. So we are going to see curve sketching, and alongside further curve sketching, that is, we are going to get the limits for the mathematics students, and we are going to proceed to the other side for the further mathematics students, which shall be precised in the course of the video. So the video is meant for all, but the only difference is wherever we are going to see further mathematics concepts, I'm going to precise. Okay, so let's begin. Let's begin with the lesson objectives. So the very first objective is, at the end of the lesson, you should be able to define and find or state the domains of respective functions. The next is to define asymptotes and understand how to find the different types of asymptotes, and also know the type of asymptotes which a curve can have. Evaluate the intercepts, study the monotonicity of a function, and find the turning point or point of inflection, stationary point, etc. And then we set up a variation table to sketch a curve. So we are going to begin with the definition of a domain. So what actually is the domain of definition? So the domain of definition is simply, or the domain of definition of a function are simply the set of points for which the function is defined. So every function has a living zone. So let's say this is a function defined by this circle. So the function knows that he can live only wherever it is defined within the zone. So once you are out of the zone, you are no longer defined. So this point is out of the domain. So if the function is defined for all points that are found inside the zone, inside the red zone, it means this is actually the domain of the function. So that's a clue of it. Now we can also define the domain of a function as, let's say, your house. So let's assume that you are under a roof, for example. Now when you leave, all you can do is at a certain time you find yourself either you're in school or in any other area, and so where you feel more comfortable is you cannot live, let's say, you cannot live, for example, let's say in a poultry farm. You might not be able to sleep well in a poultry farm because the odors there or the odors produced by the birds might be unpleasant. So the best place you will have to find yourself to live and to sleep comfortably will be inside a well constructed house. So that well constructed house can be termed to be a domain of definition in terms of where you can have a good rest. So it is a set of points for which the function is defined. So wherever the function is not defined, that point is not found in the domain of the function. Okay, so that's the domain. So now let's see the next part. So we see that the domain of a function varies from functions to functions, and we have different sorts of functions. We have polynomial functions, exponential functions, logarithmic functions, etc. So examples of functions include, we have the first, the exponential functions. Exponential functions, we have an example of an exponential function is y equal to e to the x. We also have 2 raised to the power x, etc, 3 to the power x, and so on and so forth. So those are examples of exponential functions. So another type of function are logarithmic functions. So as you can see, that's an example of a logarithmic function. We have y equal to ln of x, which is the natural logarithm. The special case, that's the ln of x is the logarithm of x in base e. So they actually represent the same thing. So we have y equal to log x plus 50. So y equal to log x plus 50. The next we can see is the rational function. So rational functions are simply functions that can be arranged in the form f of x divided by g of x. So we are going to see all these definitions such that g of x should be different from 0. So that's a rational function. So we are going to define all of this in the course of the lesson so that we see actually what it means. We have polynomial functions. Polynomial functions are simply linear functions which can always be written in the form an x raised to the power n plus an minus 1 x raised to the power n minus 1 plus, and so on and so forth, up to the last term a0. So this is the general definition of a polynomial function. So we have several types of functions in generally, in which the domain of those functions, sorry, all those functions have their respective domains. So the domain of definition of some common functions. Let's begin with the case of polynomial functions. In the case of polynomial functions like x cubed, x squared minus 4x plus 4, in other words, quadratics, their domain is simply the set of real numbers. So it is defined for all points. For what do I mean? Let's take for example the curve y is equal to x cubed. If we plug any value of x in the interval, the set of real numbers, the set of real numbers in interval notation is negative infinity, positive infinity. So it means any number can be plugged inside here. So it means if you plug any number inside this zone or inside this domain, inside this function, we should always have something that exists. Let's take for example, you can choose a negative number of your choice like negative 2. We have y is equal to negative 2, all of that cube, this gives you negative 8. No matter the number that you choose, you are always going to get an output. So it means that the domain of the function will be all the set of real numbers. So it is defined for every value of x. Okay, so we have the next, the logarithmic function. The logarithmic function, the domain of definition is all the set of positive real numbers excluding 0. So it belongs in the set x belongs to r star plus. So for the log function, the logarithm of negative number does not exist. From the graph actually can be seen, since the graph of the log function is a graph of this nature, increases like this. So what we see is it is defined only for positive numbers, so x should be positive. Likewise, the natural logarithm ln of x should be positive. So and the logarithm of 0 does not exist, log of 0 does not exist. So that's why we see the strict inequality, strictly positive. So that's actually it. So the domain of definition of any logarithmic function whatsoever that is found inside of the logarithmic function, let's say f of x, the condition is that that function f of x should always be positive for that function to be defined. So that's how we start finding for the domain, and we now solve for the values of x, which we are going to have them as points of exclusions. So the next we have rational functions. Rational functions are functions of the form f of x and g of x, and the domain is all the set of real numbers such that g of x should be different from 0. That is, we exclude all the points where the function would make sense. So what's the meaning? Let's take for example a very simple function x plus 1 divided by x, and we have to recall indeterminate forms like 1 divided by 0. This is an undeterminate form, it does not exist. On your calculator it's going to punch undefined or math error. So what we see here is, if this is a function, let's say f of x is equal to x plus 1 divided by x. So what we can realize from this function is we can plug in all sorts of values inside here, but as soon as we reach the point 0, we are going to have 0 plus 1 divided by 0, which gives 1 all over 0, which brings us back to this deadly t. So it means this is undefined. So this function will definitely be defined for all values of x such that the denominator of x itself should be different from 0. So this works for other type of functions, like for example x minus 3. So it is going to be defined for all values of x such that this function on the denominator x minus 3 should be different from 0. And so we get that this is if only if x should be different from the point 3, because at the point 3 what we get is we have 3 plus 1 divided by 3 minus 3, which gives 4 on 0. It is definitely. So in general, a divided by 0 does not exist, it does not make sense, it's indeterminate, it's an if, it's an indeterminate form where a belongs to r. Also 0 divided by 0 does not exist. So those are things that we have to know. Those are all indeterminate forms. Okay, so that's how we define the domain of definition of such functions, of rational functions. So what we do is we simply equate the denominator to 0 and exclude the zeros of the denominator. In other words, the solutions of the denominator, you exclude it from there since it's not going to be defined. Okay, now let's talk a little bit about asymptotes. So what is actually an asymptote? But before we go to asymptotes, there are several types of functions. You have trigonometric functions, etc. So we cannot list the domains of all, but in tutorial sessions, when we come across functions, we are actually going to define the domains and well explain how to come about it. Now here we have asymptote. An asymptote is a straight line that constantly approaches a given curve but does not meet at any infinite distance. So that's an asymptote. In other words, an asymptote is a line that a curve approaches as it moves towards infinity. The curves visit these asymptotes but never overtake them. So we have several types of asymptotes, and the types of asymptotes that exist are three in numbers. So the very first one is we have the vertical asymptote, we have the horizontal asymptote, and we have the oblique or slant asymptote. So these three asymptotes are of different natures and they have different characteristics. So the vertical asymptote is just a vertical line, and we represent asymptotes with dotted lines. So you have to be very careful with that, with dotted lines. So what we have is the vertical asymptote. So let's begin with the definition of a vertical asymptote. So actually, what is a vertical asymptote? We can abbreviate it as VA. So vertical asymptote has straight line equations in the form x is equal to a for the graph of a function y equal to f of x. So if it satisfies at least one of the following conditions. So what are the conditions? The first one is, and the most important is, if the limit as x approaches a finite point, that's a. So a there is a real number. A is a real number. That's a from above of f of x. If it gives you plus or minus infinity, then that point a is an asymptote. So that's the first condition. The second condition, if it approaches a from below. So what we have to do is we have to verify the non-existence of the limit at a particular point, because for the limit at the point to exist, it must be unique. So we have the limit at x approaches a from above. When we evaluate it, you should have, when you have plus or minus infinity, and when you evaluate from below, you have plus or minus infinity, it definitely tells you that that function cannot be defined at that point. So it is not a living point for that function. So that particular point a becomes an asymptote to that curve, and the special name given to the asymptote is the vertical asymptote. Okay, the next is the horizontal asymptote. So the horizontal asymptote, we can also abbreviate it as HA. The horizontal asymptote is obtained by evaluating the limit of a function at plus or minus infinity. If the limit is finite, say L, which belongs to the set of real numbers, then the horizontal asymptote is simply given by y is equal to L, where L is a real number. That is, if you evaluate the limit at infinity and it gives you L, which is a real number, then that L is the horizontal asymptote. But if L gives you plus or minus infinity, then that curve has no horizontal asymptote. For example, let's take the same curve that we used as an example. We have f of x is equal to x plus 1 divided by x. Evaluating the limit at infinity of this function, we give 1. So we see that 1 belongs to the set of real number. In other words, it is finite. So it means the horizontal asymptote, the equation of the horizontal asymptote will be y equal to 1. And so it's a horizontal line, dotted line. We represent it on the curve. Okay, so let's see the case of slant asymptote. So we have an oblique asymptote or a slant asymptote. An oblique asymptote of the graph function y equal to f of x is always in the form y equal to mx plus c. So that's actually how the oblique asymptote is. Now let us see, to find the oblique asymptote, it suffices for us to find the values of m and c. So the oblique asymptote is in the form y is equal to mx plus c, where m here is the gradient of the function as c is the intercept. So what we do is, in order for us to evaluate the value of m, we simply evaluate the limit at plus or minus infinity of f of x divided by x, and so this now gives us the value of m. If it is finite, it means that we actually have a slant asymptote. But if it gives us infinity, it means we do not have a slant asymptote. So in order for us to evaluate C after getting the value of M, we evaluate the limit as x approaches plus or minus infinity of f of x minus mx. So that's how we do to evaluate that sort of asymptote. So we call this particular sort of asymptote the oblique asymptote. Okay, now, what if they ask you to show that? Um, what if they ask you to show that that function or a given line is an asymptote to a curve? What then are we supposed to prove? So all we are supposed to show is that if we are asked to prove that, let's say, the line y is equal to mx plus c is an asymptote to a curve, then it suffices for us to prove that the limit as x approaches, let me write it to be straight, it suffices to show that the limit, sorry, the limit as x approaches plus or minus infinity of f of x minus the line, let's say mx plus c rather, this should give you 0. So if you evaluate this result and it gives you 0, it implies that the line y is equal to mx plus c is a vertical, so it's an oblique or slant asymptote. Okay. So that's what we get. Now let's proceed to the lesson. Now the next thing we are going to see are the intercepts. So what is an intercept? An intercept is a point on the y-axis through which the slope of the line passes. So there are two types of intercepts, the x and the y intercepts. The y-intercept is obtained by replacing x equal to 0 in the function f of x, and the x-intercept is obtained by replacing f of x by 0 and solving the possible values of x. Let's take again the case, let's take another case, y is equal to x squared plus 3. Let's use x squared minus 4, and you wish to calculate the intercept. So for the y-intercept means x is equal to 0, so we replace x equals 0 here, so we are just going to get y equal to -4. So it means that the y-intercept is, we have the point 0, -4. Now in order for us to calculate the x-intercept, so for the x-intercept we replace y by 0, so y now becomes 0. So if you solve for x, you are going to have plus or minus 2. That's the value of the x-intercept. So in other words, the y and the x-intercept, so you can write that in coordinate form so that y plotting you should not forget. So this is the y-intercept, -4. So the y-intercept and the x-intercept respectively, they represent the points where the curve cuts the x and the y-intercept and the y-axis respectively. So if, for example, -4 is let's say this point 4 is our intercept, so it means that at a certain point in time our curve is going to cut the point 4, something like this. And let's say this is another intercept, let's say -3, then the curve is going to cut the y-intercept at that point. So that's actually the meaning of an intercept. Now let's get the range. So the range provides the excluded region of a curve, that is, the regions where the curve cannot be found. To obtain the region, to obtain the range of a function, we use the fact that for every x in R, the discriminant should always be greater than or equal to 0. So we are expecting real roots. Now the monotonicity. A monotonic function is a function that is either always increasing or always decreasing. So those are two cases. So to study the monotony of a function, we solve the inequation f prime of x is greater than or equal to 0. So this now gives us, it's going to provide us with certain values of some values of x which we can represent on a number line to know the intervals where the function is increasing or decreasing or constant. Okay, now if f prime of x is strictly positive, then f of x increases in that interval. If f prime of x is strictly negative, then f of x decreases in that interval. Then if f prime of x is equal to 0, then f of x is constant. So we call those stationary points. Now we have turning points. So a turning point is simply where a curve turns, where it changes slope, something like this. It changes slope. Can be like this, change slope. Like in the case of quadratics, you change slope at a turning point. At every turning point, the gradient of the curve is 0, that is f prime of x is equal to 0. Let's call that equation 1. Now, if we use equation 1, we are going, in order for us to find the turning points, we use equation 1 to find the value of x. So after we have differentiated the function and equated the function to 0, what we do is we find the values of x. Then the second step, we substitute that x value in y equal to f of x to obtain the turning point. Let's say, for example, y is equal to x squared. In order for me to get this turning point, from the graph itself, the turning point is at 0 0. So what we do is we obtain y prime, that's the differential, which is 2x. And so for the turning point, you take 2x equal to 0. So this is true if only if x is equal to 0. So I'll take this 0 and I'll plug back inside this function. I'll get y equal to 0. So it means my turning point will be 0 0. So that's actually what it means for us to evaluate the turning point of that function. So that's what we get. And it goes same for all sorts of functions, so take time to differentiate the function. Now let's talk about concavity and convexity. Now a function f is said to be concave upwards in an interval I if for every x in that interval the double the second derivative of that function is positive. A function f is said to be concave downwards in an interval I if for every x in that interval the second derivative of that function is negative. And now if the second derivative is equal to 0, then the point is called the point of inflection. So we are going to see all of this in curves that we might come across. So actually we have when we talk of concave, we can have that you are concave upwards or you are concave downwards. So this is actually the meaning of something being concave. So you are actually of this nature. When we talk of something being convex or concave downwards, it's something of this nature. So that's actually we call the particular second curve is convex. So it is convex. So actually, when we talk of concave upwards, it is actually the same thing as convex downwards. So this is actually convex as seen in the second one. So that's a convex and that's a concave. So you just have to note this in your minds: convex, concave, convex, concave. So that's how the gradient will be. So in the practical exercise that we are going to do, we are definitely going to see this. And so all we have to note is all you have to note is um, all we have to note here is once you are solving, you always have to check the signs, and if it is positive, it is concave upwards. If it is negative, it means it is concave downwards. Okay, so that brings us to the end of this presentation. I hope you enjoyed the video, and please do not forget to click on the subscribe button, and just below will be the link to the tutorial video. See you in the tutorial video, and please do not forget to like, share and subscribe.